Okay, so we're going to think about how the factors need to grow, the factors of production need to grow in order to sustain growth in output, and in particular, how the the technology terms, the factor augmenting technology terms, will have to grow. Just to recap, we've been thinking about our familiar one or two factor production function, and we'll be focusing on what the substitution parameter between the factors implies for the requirements, the quantity and technological requirements for sustained output growth. So to start with, recall the simplest case of all, the one factor AK production function, and how in that case, growth is all due to capital accumulation. There's no labor, certainly no labor augmenting technology growth. And recall that in the two factor case, growth without labor augmenting technology growth, or indeed with capital augmenting technology growth, is going to be incompatible with constant returns to scale and our Caldor fact 3, where Caldor fact 3 was the constant capital to output ratio. The reason is that by Uzawa's theorem, A, capital augmenting technology, is going to be fixed. And if B doesn't make up for the fact that capital has grown by more than labor, right, the K to L ratio rising, then effective capital has grown by more than effective labor, which means that output has grown by something in between the two, which is less than the rate at which capital grew. And so the capital to output ratio is now higher than it was before. Now let's just go with a familiar CES and CRS production function. Think about the bottlenecks to growth in the gross complements case, grow negative, and the gross substitutes case, grow positive. In the long run, the growth rate of output in the gross complements case is going to be the minimum of the growth rates of effective capital and effective labor, which, as I was saying, under balanced growth, those will be equal. But if they were unequal, the growth rate of output would be the minimum of the two. Because, they're pretty strongly complementary. They're kind of like left shoes and right shoes. What you care about are pairs of shoes, and so the growth rate of the pairs of shoes is the minimum of the growth rates of the two kinds of shoes. In the Cobb-Douglas case, just by the way exponential growth works, the growth rate of output is going to be the share weighted, or at least the kind of the exponent weighted sum of the growth rates of the effective factors. And in the case of gross substitution, they're just like, different brands of white bread or something. In the long run, the growth rate of output is the maximum of the two growth rates, because, the fast growing thing is eventually approximately all of output, and it's pulling up growth with it. So, if rho is high, like if rho is 1, you can see it's exactly, y equals proportional to AK plus BL, basically. I think it's, so I mentioned the rho equals 1 case, that's perfect substitution. And it's easiest to develop intuition about the negative rho case by thinking about rho equaling -1, in which case you've got, because 1 over -1 is -1, y equals, it's like 1 over AK plus 1 over BL. So for this whole fraction to grow in a sustained way, you need both these things shrinking, both these fractions in the denominator shrinking to 0. See that? If either of them isn't shrinking to 0, if you get stuck at some positive value, because say BL stops growing, the other one might go to infinity, but then you're just left with output equaling, 1 over A times BL. or whatever one might say, times B. Okay, so in the gross complements case, growth in output, yeah, growth in output requires growth in BL. So growth in output per person requires growth in B, growth in labor augmenting technology, and growth in the capital to labor ratio. Does that make sense? You're gonna need growth in both things to sustain output at all, and then it's basically, yeah, you need sustained output to sustain growth in Y. You need growth in BL and growth in K, and so just kind of dividing through by L. Sustain growth in Y over L, you need growth in B and growth in K over L. That's just mechanical. And the question for how fast growth in output per person will be is just which is the bottleneck, which is growing more slowly, the labor augmenting technology or the capital per person. And likewise, in the growth substitutes case, you just need one or the other. And the question is which is going to be the driver, which is faster. So now we can ask how high does the savings rate have to be to make it the case in the gross complements case, how much saving does there have to be for the constraint not to be a lack of capital, but a lack of labor augmenting technology? So to answer that, let's suppose the savings rate is low enough that we're in the regime where a lack of capital accumulation is the constraint on growth. Well, in that case, the output to capital ratio is going to go to this constant. Okay, and it's kind of like in this case we're kind of in an AK economy. We've got BL growing faster, so eventually BL is astronomical compared to capital, and output's basically proportional to capital in that case. And so the output to capital ratio, it's just, in an AK world, it would just be big A, right? There wouldn't be this share parameter thing. But that's just a constant. It's just sort of a change of units. It doesn't really matter. We can just look at the production function here, right? If rho is negative, then with BL growing and AK not growing so fast, or dividing through by L, you could say with B growing and K over L not growing so fast. This B to a negative power, that goes to 0. And all you're left with is little a to the 1 over rho from the outside here times AK, because this rho and this 1 over rho cancel. Make sense? So you've got labor, but it's so plentiful relative to the capital that it's like water. It's such a negligible contribution on the margin to growth that we don't need to think about it, really. And so in this case, just as in an AK economy with explicit depreciation, the proportional growth rate of capital is going to be, so the absolute growth rate of capital is just, SY, because that's how quickly we're adding to the pile of capital we've got, minus DK, because that's the rate at which it's depreciated. And then divide through by K, so this is going to be the proportional growth rate of capital. And we just found that Y over K goes to this expression up there, little a to the 1 over rho times big A, so substitute that in, and that's our expression for the growth rate of capital. And it looks kind of familiar. Putting aside the little a to the 1 over rho, right? That's what we saw in an AK economy. It's like, you've got robots building robots or whatever, and A is how many robots a robot can build in a year. The savings rate times that is the rate at which the robot population is growing before depreciation, and that's what it is after depreciation. So this is a constrained output growth rate when you're constrained by a lack of capital accumulation. So in that regime, increasing the savings rate increases the growth rate. But what this means is that capital does not constrain output growth as long as this constrained growth rate is higher than the, so far we're taking it to be exogenous growth rate of effective labor. So as long as you're saving enough that what the constrained growth rate would be if you weren't constrained is at least as high as the exogenous growth rate of the other term, effective labor, then it can't be a constraint. That would be a contradiction, right? I'm seeing some nods and some blank stares, so maybe I should just pause for a second. We said hypothetically, let's say you weren't saving enough for, for capital not to be constrained. So you're saving so little that BL is going off to the moon, and we're in the rho less than zero world. So when one factor becomes way more plentiful, you basically have output linear in the remaining factors, or here linear in capital. So you have an AK world. We're saying suppose you're saving so little that you were just growing at the rate that the capital stock was accumulating. In that case, this would be the growth rate. And so it's only if this is less than this that the savings rate is in fact low enough to constrain growth. So rearranging, this is the amount of that's the savings rate you need to not be constrained by a lack of capital accumulation. So we'll call that condition weakly sufficient saving, and then with the strict equality, we'll call it sufficient saving. Got it? Okay. Given that you have sufficient saving, you might think, okay, well, we were considering this scenario where like BL are growing exogenously, and you're not saving enough, so AK is growing more slowly. So you might think, oh, well, if you are saving enough, then AK will grow faster than BL, right? And so AK over BL will go to infinity, right? And then the only constraint will be a lack of effective labor. That's not actually right, because even though output is linear in capital, when capital is like the main constraint, you've got lots of effective labor. Once labor starts being the constraint, then you just can't accumulate capital that quickly because the marginal product of capital starts falling. That makes sense? If you've only got so much effective labor, you can't just like exponentially accumulate the capital because capital comes out of output and there's diminishing marginal product of capital. It's linear for a while when capital is really scarce, but then it tapers off. It's just what the function tells you. And so you're going to get a steady state value of effective capital to effective labor. And you can work out what that steady state value is by remembering, what the law of motion for capital is, like we just saw on the other slide. Setting it equal to the growth rate of effective labor. So asking under what conditions will we have reached this sort of steady state of equality, and finding that sure enough, there is a so plug in a production function for y, and then rearrange, and anyway, so you're end up finding this steady state level of so flip this over and then multiply by a, and then the a shows up here, and that's taken away from there. Anyway, you don't really need to know the details of this formula, but the point is you can convince yourself with enough squinting that there's going to be a steady state ratio of effective capital to effective labor. It's not going to grow indefinitely. This steady state ratio, though, does depend on the savings rate. So in the first regime, having a higher savings rate increased the growth rate, right? The growth rate's like SA minus depreciation. Once you cross the line into the effective labor constraint regime, a higher savings rate increases the steady state effective capital to effective labor ratio, right? So higher S with negative rho means this gets larger, but then we're raising it to negative power. Wait. Higher S means this ratio gets smaller, so this gets larger. Oh yeah, so this also gets larger because rho is negative. So negative 1 over rho is positive. Yeah. So if the kind of the rate at which we're trying to, the rate at which we're diverting output into capital is higher, then there's going to, it's going to be depreciating more quickly as well because the steady state is higher. So, yeah, depreciating more quickly, but we're kind of contributing to it more quickly, and we're maintaining a higher steady state. Kind of makes sense. This is a generalization of the solid model. The solid model makes this point, but in the rho equals 0 edge case. And yeah, note that like sufficient saving, not weakly sufficient saving, but actual sufficient saving is necessary for this ratio to be positive. The case where this equality is like just met, where like expression 3 just holds its equality, is a case where you're not constrained by a lack of capital accumulation, and like the growth rate is still as high as it can be. It's still, GD plus GL. But even so, the capital to effective labor ratio is gradually falling to 0. So that is something that is a logical possibility. Now, suppose the savings rate is high enough that capital accumulation. Oh yeah, right. Good. So now we're in the gross substitutes case. So suppose the savings rate's high enough that sufficient savings equality holds, but in the other direction, like in the direction where we'd be in the effective labor constrained world under gross complementarity. Here, that'll be the world in which capital accumulation is driving growth. Because it'll be that's the growth will occur at this rate here on the left, SA to the 1 over rho times big A minus D. And that'll be faster than the growth rate of effective labor. So here we'll be in something like an AK world, because under gross substitution, it's sort of like think about the perfect substitution case. If y equals AK plus BL, but AK is growing really fast and BL is basically stagnant, then in the long run, y just basically equals AK. So the AK world is the world in which you have a lot of saving, not the world in which you have a little saving. The algebra of that is exactly as it was before. And we'll be seeing that capital accumulation drives growth unless the sufficient saving condition fails, in which case you've got to make up for the fact that you don't have any capital by just kind of having labor do the work itself, hopefully efficiently with high P. There's many reasons to believe that currently capital and labor are gross complements in aggregate. And one kind of straightforward one is just that it seems that there's probably plenty of saving and that growth is occurring at the growth rate of labor augmenting technology in some sense. I mentioned the analogy to the Solow model before. But yeah, quickly. So what about the edge case in the middle? What about the Cobb-Douglas world? Well, just looking at the growth formula for output, you might think, okay, well, the growth rate of output is this weighted average of the growth rate of effective capital and the growth rate of effective labor. So either one of them is sufficient to sustain growth in output. And dividing through by L, like GY minus GL, yeah, uh, either having capital grow faster than labor or having any amount of labor augmenting technology growth is going to be enough for growth in output per person. But that's not exactly right. And the reason is depreciation. So in the gross substitutes case, if you fix the saving rate, and if you don't have any capital, how much output you get out of each unit of capital is really high. And then as capital gets more plentiful, how much output you get out of each extra unit of capital falls. But it falls toward a positive constant. And that positive constant is that thing we keep seeing. It's the little a to the 1 over rho times big A. So that'll be the slope as you move way to the right? That'll be the marginal product of capital in the limit when capital becomes abundant. And as long as that's bigger than D, the depreciation rate, then if you save everything, you can sustain growth just from capital accumulation. You're always adding more to the amount. You're always adding more capital, and so you're adding more capital is going to be depreciating every year, but that capital is going to be producing more interest every year as well, and that the second will always exceed the first, or at least it's feasible for it always to exceed the first, given that inequality between our limiting marginal product of capital and the depreciation rate. If you save everything, then you can just keep growing. Whereas in the Cobb-Douglas case, in the Solow model case, if you have a constant exponent, little a, on capital, let's say it's a half or something, well, if you had no depreciation, everything I was saying before goes through, right? You can just keep on saving and keep on growing at a slower rate, but you'll grow without bound. But the marginal product of capital falls to zero, right? That slope on the square root, that's just falling to zero. So with depreciation, it'll eventually cross the depreciation line, right? Because it's still true that every time you double capital, you double depreciation. But you're not doubling the product of capital every time you double capital. So at a given level of technology and labor, with too much capital, net capital accumulation will eventually be zero, even if you save everything. So the Cobb-Douglas case is actually more like the gross complements case for our purposes. It's a case where you need technology to sustain growth. Capital accumulation is insufficient. Yeah.
So can you remind us, what's the thing, the solo that makes the marginal product of capital goes to zero?
The assumption of a Cobb-Douglas production function. So in a Cobb-Douglas production function, say, no matter what A is, between 0 and 1, marginal product, the tangent for K is going to 0.
And as long as rho is positive, then I can keep growing.
You need technically you need rho to be positive, and you need this thing, little a to the 1 over rho times big A minus D, to be positive. So that if you have a savings rate of 100%, you can sustain growth. I mean, you might not want a savings rate of 100%, but it'll just at least be feasible. Right. Any other questions? Okay. Okay, so what's the sign of rho? I was just saying the standard view, which I agree with, is that currently capital and labor in aggregate are gross complements. These seem to be productivity constrained rather than capital constrained in some sort of deep sense. That is to say, once you're on the technological frontier, having a high savings rate is insufficient for producing a high growth rate. For an economy that is not on the technological frontier and has a lot of people but not a lot of capital to complement them, And, people elsewhere have developed the blueprints for capital that would make all the population way more productive. Then for a long time, you can sustain high growth with a high savings rate while you're catching up. But then you'll kind of cross into the other regime, and then you'll need technological development to grow even further. There's lots of ways of trying to kind of get at this parameter, and I'm not an expert in all of them, but you can look at how manufacturers respond to changes in the ratio between the interest rate and the wage rate for the sort of people they want to hire. And you find an elasticity of substitution way less than 1. That is to say, a substitution parameter way less than 0. And there's lots of other approaches going all the way back to the paper that introduced the term CES. They're all like, yeah, looks like elasticity is probably less than 1. I think that's kind of commonsensical, right? While our capital still takes the form of tools that people need to actually put into use, people can only make use of so much capital at a given time. We only have 2 hands. The third hammer isn't going to add much. There is an alternate view, which is that actually, this whole time, capital and labor have been gross substitutes. And this is the premise of Thomas Piketty's book, Capital in the 21st Century, and a lot of other research he did surrounding it. And his only evidence for this view is that over the centuries, the sort of capital to effective labor, or effective capital to effective labor ratio, has grown slightly and gradually, but it has grown. The Caldor fact of, fully balanced growth hasn't held perfectly, but the capital share has also grown a little bit. So it's been roughly a third. I'm surprised I didn't add that anywhere, but I think that was an exercise. That used to be an exercise, and then I removed it. Anyway, it turns out it also we were pulling all those rabbits out of the hat this morning. Another thing is that the capital share will be constant under the Caldor facts, and sure enough, the capital share has been constant. In fact, that was one of his other stylized facts that I was saying you don't need, because you can actually derive it from the others. So the capital share has been roughly a third in the developed world for a long time, but not exactly. And if it's been moving, it's been rising. And the gross complements model would imply that they should move in opposite directions. As capital gets relatively more plentiful, its share should fall. Again, it's starting to turn into something like water, which is so plentiful and cheap that its share is almost 0. There's lots of ways to reconcile this, though, with the other sources of evidence we would have for gross complementarity. So, the production function could be changing in small ways over time, like that little a share parameter thing could be changing, so that at any point in time you have gross complementarity, but something else is nudging the share a little bit, and that's kind of producing the effect that the Kenny notes. We don't really need to get into this, but basically the idea is if you have a lot more capital, you'll want to use a more capital-intensive production process. And that can lead to a higher steady state ratio of effective capital to effective labor. Anyway, so Chad Jones has a paper laying out how this can work, and there's a lot of work on directed technical change, how the shape of the production function will respond to the availability of the factors. A point that I think is Yeah, okay. So anyway, so suppose it's the case that in the short run, the factors are gross complements, but in the long run, they're gross substitutes because in the long run, we develop kind of ever more capital intensive production processes so that like if you just give it enough time, you don't need any growth in effective labor. We can just have capital take over. It just sort of requires this process of changing our production technology, right? What that would imply is that in the long run, in the short run, you would see like if we suddenly have an influx of capital, sure, we have a lower capital share. But in the long run, this is offset by this reorganization of production to make effective use of all this extra capital in a way that like doesn't lower its marginal product a lot. So if the relative price of capital falls by 1%, to put this kind of in reverse, we'll figure out ways to make productive use of capital such that we end up using more than 1% more than we were using before. The big implication of this would be that if rich people sort of pile up the capital indefinitely, their incomes as a fraction of GDP will rise, and this will be a big driver of overall income inequality because capital ownership is very unequally distributed. Rich people own, you know, even um, uh, yeah, the top 10% of households by overall income have like more than 10% of um, sorry, if you look at like the cumulative distribution function and you look at the people who have like the top 10% of the income, they have more than the top 10% of the capital. So this would, yeah, a shift toward a higher capital share would tend to increase overall inequality. Anyway, I think the point is sensible that elasticities of substitution will be a lot higher in the long run than in the short run when as people have time to adapt. Like in some sense, maybe a given production process has just some like factor ratio and they're like perfect complements. You have things set up to like use so many people and so much equipment. And in the long run, you adjust. But it's still a really uncommon view that even the long run elasticity substitution we've seen over the last century or two is so high that the factors in some sense have been gross substitutes all along. So at least one paper, like very explicitly, is responding to the Piketty point, and they find, yeah, the long run substitutability is higher than the short run, but it's still negative. And yeah, again, we're gonna see sort of incidentally as we go along dynamics that can produce an increase in the effective capital to labor ratio alongside an increase of the capital share without implying that we've had gross substitution this whole time. Just keep an eye out for that tomorrow. Ron.
It would reconcile the still negative long run row with the fact that we have forward the capital share and the capital labor ratio will be the same direction. What's the
So just I actually don't remember, but I can tell you I think it's going to be some version of what we'll see tomorrow. So can we talk about it more tomorrow? Yeah. So yeah, we'll just follow the kind of conventional assumption that the two big factors are gross complements until, of course, we're discussing how AI could change that, right? But I think this is important because like you have to think that if you're going to be predicting big changes after AI that's like powerful enough to make capital a gross substitute for labor, you've got to think it's not already a gross substitute for labor. Now, so yeah, so we kind of started talking about an AK model. Let's think about the other extreme in which we say, yeah, we're basically constrained by effective labor. So let's just say that output is, it's just proportional to effective labor. If we have sufficient saving, so we're in the effective labor constrained regime. And yeah, we have gross complementarity. In some sense, this isn't such a bad model, right? It straightforwardly captures this fact that effective labor is historically the main constraint on growth in the developed world. That, yeah, most output, like 2/3, as I was saying, is paid out as wages. That saving more won't increase the growth rate. And why not? Because like for an individual household, it looks like saving more makes them richer. Well, because it enriches the saver mainly at the expense of other savers, right? One saver piles up more capital, but they're just decreasing the marginal product of capital for everyone else. And yeah, you're increasing the steady state capital to output ratio, but you're not affecting the growth rate. And so if you zoom out enough that you're just caring about the long run growth rate, saving on the margin adds nothing at all. Yeah, let me just get through this quickly. So what is this B thing? I've been calling it labor augmenting technology. You could also, on some level, maybe think about B as indexing human capital, like how educated people are and so on. But a key difference there will be that technology is non-rival, and so it gives rise to these like intense returns to scale. One new idea that's a new, it's a new like idea for how to organize production in a way that doesn't require as much labor, that increases B for everyone that uses it, for every factory that adopts the blueprint or whatever. Whereas human capital accumulates in some sense like physical capital. You have to build it for each unit. You have to teach each student. Yeah, the idea that B has been growing exponentially also is arguably kind of weird, kind of an extreme assumption. It implies that for generation after generation after generation, marginally like better educated parents and teachers can sustain proportionally better educated children, even in the absence of any new kind of general purpose, things to teach them. Of course, in practice, both things are necessary. Developing new technologies is kind of useless if no one knows how to use them. Maybe a reconciliation could be that technology growth raises the ceiling on labor productivity, but then people have to sort of catch up to it by, realizing their productive potential. But on this view, then like as long as people are sufficiently educated, kind of like with the saving point, right? As long as people are saving enough, well, as long as people are investing enough in their own capital, or if their countries are investing enough in their capital or whatever, the bottleneck is still going to be technology. So for simplicity, we won't think about that. I mean, we're thinking about AI anyway. So we'll just talk about B when it comes up at all as just labor augmenting technology. And finally, there are other things that contribute to growth that people will sometimes hand-wavily roll into B if they want to kind of have a stylized model reflect all of these other important determinants of growth. And yeah, I mean, again, this won't come up that much, but I think it's probably cleaner to not think of them as B, but as like potential bottlenecks to the accumulation of capital or the development and deployment of technologies. And that as long as they're sufficiently functional, the bottleneck to growth is technology in a more straightforward sense. But anyway, just sort of flagging that depending on what literatures you're reading or who you're talking to, this very nebulous, stylized, abstract thing that is, productivity or labor augmenting technology can sometimes have different explanations under the hood. Okay, so let's take a 15-minute break and come back at 3:15. Okay, so labor augmenting technology's been growing. It's been growing at 2% a year, and that's been driving output growth, or growth in output per person at 2% a year. Why has that been happening? Well, it'll be modeled in different ways in different papers for different purposes. But one thing you can do is just suppose that it's happening exogenously, not necessarily that you believe that it's just falling from the sky, but as a modeling assumption, you might just kind of posit exogenous technology growth. You could have a model in which various sort of economic outputs contribute to the growth in labor augmenting technology, and that allows for more output, and that feeds back into more technology growth. The whole system is sort of closed. Or you can have a semi-endogenous model where technology is growing as a function of other variables, in particular population, more people coming up with more ideas, but at least in the long run, sustaining growth in technology requires this sort of force being fed in from the outside, this exogenous population growth, which you're not going to model. You're just going to say people just feel like having children, and that's not like an economic decision within the model, and that leads to population growth. So very, very broadly, these are kind of modeling choices you can make. An example of an endogenous model would be a learning by doing model. In particular, a narrow kind of learning by doing model, which is enough to sustain, say, exponential technology growth without any population growth. So let's say that as people go about their work, they sort of incidentally discover more efficient ways of producing things. And so the absolute growth rate of labor augmenting technology is proportional to the rate at which we're producing. It's proportional to output. Divide through by B to get the growth rate, the exponential growth rate, labor augmenting technology proportional to that ratio there, output to labor augmenting technology. So what does this imply? Well, for one thing, maybe we should look at the second line first. Fixing the savings rate, output is just going to be proportional to BL, basically, right? That's what we saw. You've got that steady state ratio of effective capital to effective labor, but they're both growing at the same rate. You've got your balanced growth, output, effective capital, effective labor, all growing at the same rate. And so fixing the population, so we're fixing L now, Y over B is growing at, Y over B is constant, because like Y is growing at the same rate as B. It's growing at the same rate as BL, but L is constant, so it's growing at the same rate as B. So Y and B are growing at the same rate. And because Y over B is constant, sure enough, GB is constant, which is what we said. B is growing at a constant rate. That's the same rate as output is growing. But here, unlike in the exogenous technology growth case, saving more increases the steady state growth rate. Why? So not through the direct channel, that higher saving means that we have more capital to produce with. Through that channel, you have this issue, right? You just, and it's even worse than the Solvo case, right? With capital and labor being gross complements, the marginal product of capital flattens out and sort of rises toward a ceiling. So the overall product of capital rises toward a ceiling as capital grows. So anyway, that's still true here. We're not changing the production function. And yet, increasing the savings rate will increase the steady state growth rate because you'll have a higher steady state like capital or effective capital to effective labor ratio. But that means by CRS, output will be higher by something kind of intermediate, something in between this like this higher amount of effective capital and the initial level of effective labor. So yeah, so more saving pushes up output, it pushes up output in the unit of labor augmenting technology. So from that simple formula, you see it raises the growth rate of labor augmenting technology. But like the mechanism is hopefully kind of simple. We save more, we produce at least a little bit more, and every unit we produce contributes to technological development. So we grow faster. Learning by doing models are often motivated by the observation of what are called experience curves, where you take a particular good and you plot how productive we are at building it as a function of how many we have produced, right? So just looking at line 10, that's looking at the growth rate of productivity as a function of the rate at which we're producing. But hopefully, if we start at like some B0, to figure out what like BT is going to be, you can just integrate, how much we have produced, and you can, so the cost of the nth unit will just depend on n. It just depends on how much we've produced so far. So that's explained a bit in the appendix at the end of these slides. But like a really kind of famous example is when it comes to solar panels. As we have produced more of them cumulatively, the prices come down. And this graph actually doesn't really display something interesting I have in mind very well, but it turns out that when you try to distinguish between the effect of time and the effect of cumulative production seems to be the main contributor. Does that kind of make sense? So like again, I wish I had a better graph, but like time's not showing up here, right? Except in the indexes on the line. So but like let's say we banned solar panels for 100 years. And then we started producing them again in 21, 25. And the price kept coming down. Then you would just see an uninterrupted straight line. Over time, it would be coming down, it would be flat for a while, and it would be coming down. And that would be telling you that it's not that there's something else going on. Like we've just been sort of getting more efficient in general. We've been developing better like management techniques or something, and that's been bringing down the price of everything. We say, no. It's a real learning by doing effect, where the process of producing solar panels teaches us how to do it cheaper. And that is kind of what we find for some things, including solar panels. Yeah, I see your hand. Remind me your name again. I'm sorry.
Maxime.
Maxime, right.
Multiple things. So like with this, it seems to me, I mean, of course, reverse causality, right? But like.
Yes. So that's exactly what I'm getting at here. So it could be that if you're producing more, or you anticipate you're going to have to produce more, there's more of an incentive to figure out a way to produce it more cheaply.
Yeah. And I would expect that there's just, simply because you can, offer it as a cheaper price, right? More is produced, right? Like the demand is higher.
Yeah, that's also a good point, for sure. Oh. Right, so as I was saying, so you can kind of, you can write down the model and it can sort of fit the data, but it doesn't necessarily explain the mechanics of what's going on. Like it's a little bit weird and suspicious on some level that just like, by producing, you get new ideas, maybe sometimes, but often you need to like put an explicit R&D effort and do experiments that you don't accidentally wind up doing for yourself as you're kind of doing trial and error. Yeah, as you were just saying, you can explain the empirical relationship in other ways, like the reverse causality thing, where you invest more in lowering the price of something because you know that you'll have to produce more, or you're able to sell more when it's cheaper. So in terms of how to like model technological development development at least a little bit more explicitly. Starting with the classic Romer model. This is the view that technology grows because people do research. Say some fraction S of the population does research, S for scientists, if you like. We'll say that just as B makes people more productive at making final goods, so if B is double, it's each factory worker counts for 2, the same is true in research. That's the Romer model. And because B dot, these new ideas, grow in proportion to the research inputs, the SL, people that are doing research, and then they're augmented by B, GB is going to be constant for a fixed population and a fixed share of people doing research. So you have a fixed population, say 10% of them are researchers, and they sustain this exponential process, right? Because they're getting more productive as they're going along. You can put a lambda up there or not. In Romer's original paper, he just had lambda equaling 1. But there's no deep reason to expect constant returns to scale in the case of R&D, because 2 copies of the same idea are no more valuable than 1. So remember, the replication argument was the reason for assuming constant returns to scale in production. But if you have like double the researchers, but they're all working on the same technological frontier, to some extent, they might just come up with the same idea twice. And indeed, that's the whole virtue of technology, is that like you don't need to bother making it over and over and over again for every like factory or whatever. One is just as good as infinitely many. The recipe is all you need. But by the same token, you have no reason to expect that like scaling up the number of researchers on a given technological frontier, on a given level of B, linearly increases the rate at which you make progress. And you can account for that in a simple way by sticking a lambda on there. So if lambda is less than 1, then there's some risk of people kind of duplicating effort, some rate at which they tend to. So B grows exponentially, just as we've observed. However, if the population grows, and or the share of people doing research grows, if that can't grow indefinitely, of course, it would run into 100%. But I mean, starting out so low, it could grow at a fast rate for a long time. So if the total research population grows, the rate of growth, the exponential rate of growth of labor augmenting technology will itself rise without bound. And that has, so kind of this has been happening, and this has not. And that motivates the Jones model, which I'll get to on the next slide. First, there's this question of what lambda should be exponentiating. I noted that research might sort of be imperfectly parallelizable in the sense that it might be better to have one team working for 2 years than 2 teams working side by side. It might be better. I mean, they might get more done because some things have to be done in sequence, and if you try to parallelize them, you end up just kind of duplicating work or whatever. Another reason why you might want a lambda less than 1 is that if you imagine shifting people over from production to research, the people with the highest comparative advantage in research will tend to be selected first, probably. At least that would be the efficient thing. And so you're going to be getting ever less research done per unit of production that you forego as you raise that research share, as you raise S. Now, if that's the only effect, if there's no stepping on toes sort of thing, then you just want the lambda on S. Does that make sense? So if you double the whole population, you'd be doubling the number of geniuses alongside everyone else. But if you fix the population, but you double the number of researchers just by kind of dipping kind of lower into the pool, then that's raising S to not L, and that's going to be less effective. And if you want to capture both of these effects, that's fine. Obviously, you can put both exponents on there with the exponent on. This is backwards. Lambda 1 should be less than lambda 2. Okay. Because they're the effects are multiplying each other. Yeah, I guess for now we'll typically just follow the standard convention. And this won't matter if we're just going to assume a fixed S, which we'll also do sometimes. Okay, so I was saying a kind of crazy implication of the Romer model is that the growth rate of technology and thus of output, or output per person, should itself go to infinity if the research population grows, and sort of grows without bound, and the number of researchers there are in the world has grown by many, factor of 40 or something in the US at least. I think there's about 40 times as many researchers in the US now as there were in 1930 or something like that. And obviously, the growth rate has not been multiplied by a factor of 40. In fact, if anything, it's declined a little bit. This motivates the Jones model. So this is going to be a semi-endogenous model because sustaining growth is going to rely on sustaining population growth. The Jones model has one little tweak from the Romer model, and it's that beta. Beta represents the second big way in which developing new technologies is fundamentally different from developing new goods or developing more copies of final goods. And this is that every new idea is different. So this is, again, it's just kind of another implication of the same point, right? Because technologies are non-rival, the whole point is, each person coming up with a new idea for how to produce things more efficiently. Everyone can benefit from that idea. And that's great, but it means that we have no reason to accept the replication argument, and so we might want to stick a lambda up there. But it also means that developing the 10th idea is just a different project from developing the 5th or the 9th. Whereas building the 10th car is exactly the same project as building the 9th, if it's the same model, just cranking them out of an assembly line. And in particular, developing the 10th idea might be harder than developing the 9th, because you pick the low-hanging fruit first. So you might see some negative feedback. This isn't denying the fact that the technologies we've developed so far assist us in the development of further technologies. We still have that b on the right and is raised to a 1. But it's just offsetting that partially or fully or more than fully is the fact that ideas can get harder to find over time. So beta can be less than 1 or equal to 1, more than 1. Suppose that S is fixed, but the population grows at rate GL. You're going to need population growth to sustain growth in S out, right? Because S can't grow forever. S is just between 0 and 1. So let's just say S is fixed. We've got this long run growth in population. There's going to be a steady state growth rate of labor augmenting technology. And to find it, you can ask, what growth rate of technology would make the growth rate of technology 0? Because the steady state GB will be obtained when line 13 is not changing. If that expression on the right is changing, we're not at steady state GB. And how quickly is this term on the right growing? Well, remember our growth rules about exponentials. Again, briefly touched on the slide this morning. Go back to it if this isn't like second nature to you, because you're going to see it over and over and over again. But you just, you pull down the exponent you pull down the exponents and you turn multiplications into additions. So the growth rate of B is this. Negative beta times growth rate of B equals lambda times growth rate of B. When will that be 0? Precisely when B is growing at lambda over beta GL. See that? And beta GB divided by lambda. By the data. Yeah.
For our purpose, what's making it semi here?
The fact that we're not modeling why L would grow. We're just stipulating that L grows.
And how is it different in the previous case?
In the Roman model, we were assuming a constant population. So I was saying, if you have a constant population, you have constant GB, because there was no beta here.
I guess my point is beta and lambda, they're all related to the production of science and production of knowledge. To me, they're both hyperparameters, they're both non-endogenous in a sense, and then the rest is endogenous. And to me, it's we're just fitting the data, and like Jones is a different argument that the science is like doubling, but the output is not. And then to me, I don't see why it's necessarily not fully endogenous.
It's not fully endogenous because when you write down how the model works on a bunch of lines, you just write GL greater than 0, and you don't write L as a function. I mean, so okay, it's definitely a you're right. There's a definitely gray area in the sense that you can say, okay, well, L dot is a function of L. It's just some portion, it's like it's like 1.1 L. Everyone has 1.1 kids on average or something. Or per like woman say it's 1.1. It's only a very kind of threadbare sense, endogenous there. We were saying that like we're not letting anything depend on how many children people have. It's not like more output gets turned into more people because of it's just we're just saying there's no optimization. It's like in the solid models, just you have an exogenous savings rate, right? We can reverse engineer what would give rise to a constant savings rate, but let's say constant rate of child growth, constant savings rate. That part we're basically just taking for granted. That part will be exogenous, and we'll let that drive growth. I mean, in practice, these things don't really, words can take on meanings of their own. And in practice, I maybe shouldn't have even like framed things at this level of abstraction. What I should have said is that this is the way everyone uses the terms. Endogenous means with a constant population, you get a positive exponential growth rate of technology, and semi-endogenous means you don't. But you do with population growth. So what are beta and lambda? Okay, so in the Jones model, at least, we know the ratio. We know lambda over beta is the thing you multiply GL by to get the rate of technology growth. And so this paper, our idea is getting harder to find from a few years ago, does this sort of calculation. And obviously really simplifying, but basically the point is, while the number of researchers has been growing at like 6% a year, and output per person, aka equilibrium labor augmented technology, has been growing at like 2% a year. So lambda over beta has been a third. they're hard to measure independently, but at least we can rule out the Romer case of beta equals 0, because we've been sustaining this growth in the number of researchers to the point that like it's gotten multiplied by a factor of 40 over the last couple of generations. And GB hasn't gotten done, certainly hasn't multiplied by a factor of 40. So, you know, yeah. But by the way, you see what's going on with beta equals 0 in the Romer case? Beta equals 0. It's not that we instantaneously get infinite growth in B. It's that the steady state growth rate of technology is infinite in the sense that the growth rate just rises and rises. Okay? So that's kind of the Jones view of the world. You can have other explanations of the growth rate and the number of researchers, along with the lack of acceleration in technology growth. For instance, Patrick Collison, in an interview with Tyler Cowen from a few years ago, argues that maybe Romer is right after all, but now there's just so much red tape that each researcher gets like 1/40th as much done. And he points out that, you know, when you compare how much it costs to build the Golden Gate Bridge versus building a bridge today, or like subway lines in New York a long time ago versus today, some of that stuff also is 40 times more expensive now. And he sort of mockingly asks, have beams gotten harder to lift? So his implicit model, as I would interpret it, is that theta thing that I've just been sticking in the equations but not referring to, that coefficient saying that like the thing on the left is proportional to the inputs on the right. That's some kind of like R&D specific, like R&D industry specific productivity term or whatever. And that's been falling like a stone. It's like a 40th now what it used to be. I think that's basically what Patrick Collison would say. You know, so that's, yeah, I mean, that's been falling as fast as the research inputs have been rising. And, you know, he and Tyler were keen to start a sort of movement they called progress studies to see if they could reverse that trend, because, you know, even if it seemed like a long shot, 40% faster growth would be a big deal. 40 times faster growth. Note that more red tape isn't necessarily inefficient. It could be that as we get richer, we just value safety over consumption. And so we don't want to let our mad scientists, you know, plow ahead as recklessly as they could a couple generations ago or something. And we'll talk a bit more about that next week. Obviously, also super relevant to transformative AI. But for now, we'll typically assume the Jones model that beta is greater than 0. You know, maybe lambda over beta is not actually a third. Maybe it's, you know, a half, and the red tape thing makes up the rest of the difference. But full on beta equals 0, I think, is probably yeah, probably wrong. I mean, and you know, whatever. You can get all into that argument, but I think you can, if you can cherry pick a few case studies of bridges and things and make it seem like this 40x thing is the more general phenomenon. But on the whole, I think R&D is pretty unique, as you would expect it to be from first principles, because the 40th idea is just, you know, again, different in the way that the 40th car is not. Yeah, Kron.
The way we think about B accumulating is we have more scientists and then these more ideas. Things work well for your.
Sorry, I missed a word. You started.
The way we're thinking about B or like technology, so it's still accumulating, which is more scientists, more ideas.
Yeah.
B accumulates. Things work fine for like technology. Also, but if we were to think about the other like slightly fuzzier institutions, culture type.
Yeah.
Interpretations that you have.
Yeah. No, I agree.
Do you have any like mapping from where we have a high population to like either institutes or culture get? I mean, sure, like people come up with better ideas, but
no, I.
The red tape is it's like more like this. Look, one input in the B is actually like this red tape is function reducing B, and that happens with the population. Right? Maybe there's a sense in which growing population is going to be uniform.
Yeah, I mean, I think that's a great question. It's so in general, I think it's hard to like actually estimate the effective population on like uh technology at all, let alone like sort of nebulous varieties of stuff that's kind of like technology, like institutions. But one thing that comes to mind is that really, really long run growth paper from Kramer about how if you look at uh, you know, Tasmania, Australia, Eurasia, Africa, and the Americas. The ordering of how many people were in a given sort of connected region of the world sort of was increasing in its the rate at which the population grew in each region, which was his proxy for the rate at which technology was improving, because as technology improved, that basically just meant ability to support more people. And that was, it's a Malthusian model. So better technology means more people. Anyway, the rate at which technology grew as proxied by more people took the same ordering as the initial like number of people. And even though he's not looking at institutions, the institutions totally followed, right? Like uh, as countries sort of develop uh, the institutions associated with like cities, for instance, and then um, states and empires and all the rest of it. That it's not like Tasmania raced ahead with the empires, but they didn't have the people. So other than that, I'm not sure how you would estimate that, but maybe you have an idea. Or okay, yeah, great.
Yeah, I mean, the question was kind of like, can it also be some like not monetary, but kind of valuation effect that kind of like the idea that essentially like all the innovation is concentrated in some sectors, and in those sectors actually things progress very, very, very well, but like those sectors just become less and less important for the overall economy, right? Like, like semiconductors are super, super important, but we just pay less and less for semiconductors. And so it will look like GDP does not grow that fast, right? As maybe before, because before, was more important to get more productive in semiconductors. Do you know what I mean?
Well, no, I see what you mean, like in that there could be this shift from domains in which growth kind of actually contributes to GDP in a way that that we pick it up, to other domains in which we're growing in ways we like just as much, but it's just like not getting reflected in GDP. And so I mean, again, I think it would be pretty extreme to think that like we're kind of growing in like 40 times faster now, and that all of that is not accounted for properly. But yeah, and qualitatively, I get that point. The semiconductor point, I don't think that would follow, because I don't think semiconductors are providing huge like positive externalities that we're not accounting for really. They're very concrete like rival units that like we pay for, and yeah, they're getting way cheaper, but that's reflecting the fact that the marginal value of computation is falling. I think that's kind of an interesting obviously, yeah, they're really useful, but on the margin they're getting less and less useful because we have a lot of them and we're not kind of scaling up the things that complement them as quickly. That could turn around once we come up with the software that allows semiconductors to like take over from like all human brains or something. But for now, I think this is kind of an interesting point, and I want to actually dwell on it for a second. There's this very optimistic way of putting Moore's law, which is that like, the technology is advancing so fast that the price of computation is like halving every 18 months, right? But there's this other way of putting Moore's law, which is that we're so rapidly running out of useful uses of computation that the marginal value of computation is halving every 18 months. And
But that means kind of like we might be very productive, in certain sectors, like in innovation, but for some reason, we might, enjoy, I don't know, croissants or something, and those croissants are not getting more productively, or like kind of, we're not getting it producing them, right? And so,
but that's
if you don't pay anything for semiconductors anymore,
yeah.
I mean, that doesn't mean that the research effort itself gets less productive, right?
Well, it gets less productive at like producing things that we value in some
Right.
sense. Yeah, yeah.
Just briefly on this, I think it's worth noting that the blue paper looks at semiconductors in particular, notes that the researcher returns are decreasing. So yeah.
Oh, sorry. Yeah, thanks for noting that. Oh, but interestingly, right. So you can look at lambda over beta. We'll get all into this next week, but we can look at lambda over beta by industry, right? Because you can say, okay, for like the economy as a whole, yeah, this is 2%, that's 6%, whatever. So lambda over beta is a third. But Moore's law, you can say, this is like 70% a year, say, right? Because like every year and a half, it's like double. So that's huge. That's 0.7. That's not been sustained by a constant number of people working at Intel and NVIDIA and so on. It's been growing. But how fast has it been growing? Only 1/5 as fast as the 0.7. So it's not like the number of semiconductor researchers has been doubling every year or anything. It's been growing at like a few percent a year. And that's been sustaining a 70% growth rate in the productivity on that front. Right. And so the lambda over beta is 5 rather than a third for semiconductors. So that's the closest to Romer of all the things they look at. But this is more evidence for like their view as opposed to the Romer view, is that it's not just like in aggregate that you find this relationship. You also find it in like semiconductors and calories and medical innovations and so on. You can also have a lab equipment model in which capital contributes to R&D. If capital and labor are gross complements in R&D, then assuming kind of something like efficient saving, then that's not going to matter too much. But of course, we're going to be interested in thinking about the case in which there's lab equipment that can actually grow substitute for labor in R&D because it's fully, or at least approaching full automation. But just kind of keep that in mind. A lab equipment model is one in which capital features in R&D. Yeah.
So the Moore's law points, so it's like there's this battle between like, either we're getting like much better at producing some conductors or we're running out of users with them.
Well, not either or. I mean, it's
or combination or something. My point is like, can't we just like look at quantity to tell which stories happen?
No. The quantity could double every year, but the price could stay high, and then it would just kind of like come to swallow GDP. So the interesting thing is that both things are true. The quantity's been rising. Like the amount of compute in the world has been rising a lot. And the price has been falling.
That seems like you can explain that with us just getting better at producing something.
No, because so the price, you need to think about it in like what's the numeraire? Let's think about apples, say. Okay, so let's just denominate prices in units of apples. How many apples are we willing to give up for like computation? If we had a technology that could turn computations into apples, because like we had a bunch of bots lying around and like we could, if we just put the chip in it, then it could like go and plant apple trees and harvest them, whatever. So we could, each flop could just turn into an apple, right? Then even as we got loads and loads of flops, the price of a flop would not fall, keeping apples as the numeraire. If it was just apples, the price of apples would fall relative to other things, but put that aside. So we just get a lot of growth. We get a huge increase in the number of flop. The price would not fall. We just get a lot more growth. As it happens, both things have been happening. We're getting way more compute, but because we're not able to turn them into apples or really anything else that matters at a constant rate, the price has been falling really fast. The interesting point is what'll change once we keep on being able to ramp up all this compute, but it stops getting useless really quickly, because actually like it can start like turning into apples and so on at a rate that's not diminishing really fast. Okay. Anything else on that? All right. So briefly, just to familiarize ourselves with the terminology of level and growth effects. Suppose there's some shock to one of the exogenous variables, like there's just a bunch more capital, or population starts growing at a different rate for some reason. We say that induces a level effect if it makes output per person proportionally higher or lower in the long run than it would have been before, but it's just always like some proportion off. And it's a growth effect that induces a lasting change to the growth rate itself. So yeah. And just sort of to make sure we know what we mean here, if future output per person changes by a proportion that itself shrinks to zero, right? Even if the change in output per person does not shrink to zero in absolute terms. So if everyone gets like one more apple every year from now to the end of time, but what they would have had without the shock is growing over time. So that one extra apple is sort of shrinking to zero in proportional terms. That's, you say there has not even been a level effect. Here's a way to visualize them, right? So if you've got your baseline path of output growth, then the level effect is you're always say double what you would have been. In long terms, that means you're always a constant higher, there's always a constant proportion higher. And the growth rate rises while you're shifting to the higher path, but then the long run growth rate is the same. For growth effects, the long run growth rate is higher, which means the proportional gap is itself growing over time. Okay. So before we were assuming CRS production, so there were no scale effects. Two Earths had double the inputs and double the outputs, and we could use Euler's theorem to divide the pie under competitive circumstances. By contrast, research, as modeled here, introduces scale effects, because doubling the Earth means you've got double the researchers. You've still got CRS in production, but now we're ramping up the productivity ideas more quickly. And so output will eventually be more than twice as high across the two planets communicating with each other than it would have been on the single planet that didn't get all these extra researchers on the other planet to learn from. One implication of this is that we can't all be paid our marginal products. I kind of think this is a funny point on some level, like it's very common in academia for people to feel like they're not getting paid what they're worth, and it's maybe true, but it's impossible to pay everyone what they're worth. Research is probably going to be a public good. Depending on how patents work, it can be under or over provided, actually. We'll see a little bit about this at the end of this week. But you can kind of see how it's just a classic public good, right? A new idea, everyone gets to benefit from it. Either you're going to keep it a trade secret and make a profit off of it. That's going to be really inefficient, or there's going to be underinvestment in new ideas because you can't capture all the benefits. And so if you want to figure out what the optimal path of research investments over time is, you can't just rely on prices. You're sort of going to have to write down an explicit optimization problem. Another implication here is that fertility is going to be a public good, right? At least if the kid has any chance at all of coming up with a new idea that we all like. Okay. Yeah, just because we're sort of out of time. This stuff is, it's good to like kind of know the terminology, but it's not something we'll be like really intensely coming back to or anything. We'll just be like dealing with the math of the models more at face value. There's some kind of, you can sort of test your intuitions about these models by imagining different shocks and then asking, under what conditions does this produce a level effect or a growth effect? And that's the exercise I've put down for this lecture if you find it helpful. But that's that. So to recap, to match the Caldor facts, you need that balanced growth. So if you're gonna have growth in output per person at 2% a year, or whatever, you need B growing at 2% a year, and you need AK growing at PB plus GL. In the gross complements case, you need growth in both terms to sustain growth in output per person. In the gross substitutes case, you only need one of them. We're probably in the gross complements case, though Zach actually has some content I think he'll share in the Slack about someone besides Piketty who thinks that actually in the long run, capital and labor gross substitutes. So maybe it's not as fringe of an idea as I was making it out before, but it is the minority view. And yeah. Yeah, and we went through some growth models and we thought about returning to scale. That's that.